Okay, so welcome back after that long winter break. Um, so today we'll continue on kind of things that we've been doing. We've recall that we're still doing electrostatics problems. Um, we've developed some PDE theory which we use to solve a couple of electrostatic problems. Um, so recall that from the PDE theory we have learned, we know how to use the Bessel I functions and the Bessel J functions at all orders. So IL and JL we know how to use, okay? And those we found were the eigenfunctions of the Laplacian. We also found the solutions of zero eigenvalue problem of the Laplacian, which is basically solving the Laplace equation, which are the spherical harmonics, which is the first thing we did, okay? So today I want to solve a set of problems which not a set of problems. Today I will solve one problem, okay? But I want to illustrate a certain thing using this problem, which is the method of images, okay? So if you have solved Griffith's problems, you might have seen that the method of images is a very ingenious technique to solve many different problems. For the first time you might have seen the method of images is to solve for a point charge over a conducting plane, okay? Then what is the potential above this conducting plane? Then you use the uniqueness theorem and so on and say that to solve this problem, all you need to do is to take the point charge q on top, which is over the conducting plane, and you just reflect it around this conducting plane and put a minus charge, minus q at the opposite point, the mirror reflected point, okay? And the potential on top is the potential due to these 2 point charges, because that satisfies the boundary condition that potential is 0 on the plane, and it also solves the correct Poisson equation on the top, right? So that was the method of images. But then in that case, the method of images is fairly straightforward. And you can also go on to do a sphere, a conducting sphere problem, which is also sort of straightforward. You can find the mirror charge and the position of the mirror charge. But then you come to dielectric problems and planar dielectric problems. This problem of vacuum on top of z equal to 0 plane, and below the z equal to 0 plane, it's filled with some dielectric constant epsilon, right? There also you can solve it with the method of images problem, as a method of images problem, and Griffith sort of gives you the reflected charge at the reflected position in this problem. But you might wonder, how do you get to that, right? How do you straightforwardly from PDE theory sort of derive the method of images, and how do you show that it is correct, other than the fact that it actually gives right answers somehow, okay? So that's our agenda for today. I want to sort of derive the method of images from PDE theory, okay? And the claim is that all that we have learned so far is really enough. Actually, just J0 is enough. The Bessel J0 function that we derived and sort of studied a few classes ago is all you need for the method of images, okay? So let's begin by solving this straightforward and simple problem of the conducting plane, okay? Point charge over the conducting plane, point charge conducting plane, and the method of images. Okay, so the problem that we're going to solve first, for me to sort of derive the method of images for you, and from there you will see how to use it for other problems, okay? So for the problem I want to start with is the following. You have a conducting plane, an infinite conducting plane, okay, which is grounded. So this is an infinite conducting plane which is grounded at z equal to 0, okay? And you put a point charge q at some distance, say z0, okay? The point charge q is at 0, 0, z0 in Cartesian coordinates, okay? The question is, what is the potential everywhere, okay? Now you might scream, just put a minus q at minus z naught, write down the potential, the Coulomb green function for each of them, and we're done, right? So we know that the answer is, we know the answer by the method of images to be that the potential at some rho comma z is equal to 1 over 4 pi epsilon naught, actually q over 4 pi epsilon naught, times 1 over square root rho squared plus point charge at z naught and the opposite point charge at minus z naught. Okay, we know that this is the answer. Okay. Question is, how do you get to this answer? Okay. Okay. So let's try to get to this answer. Okay. First of all, what is the physics of this problem? The physics is you take this infinite conducting plane, okay, and you put a point charge plus q on top. This plus q will induce a negative charge density on this conducting plane. Okay, so it will induce some charge density here. Okay, and the potential at any point above is the potential due to this plus q and the induced charge density. Right? But notice that the induced charge density should be axisymmetric, should be symmetric about the z-axis, right? Because it's an infinite plane and there is a symmetry of rotation along the z-axis. Okay, so this is really an axisymmetric problem which we did a few classes ago, right? So then what it means to say that it's an axisymmetric problem is that the potential has a certain representation in terms of the vessel J0, right? Okay, so let me be more clear about what I mean. Okay, so let's write it down. So the potential at any point is due to the point charge q, which is basically the Coulomb green function 4 pi by q by 4 pi epsilon naught square root rho squared plus z minus z naught whole squared. Okay, and due to this surface charge density sigma. Okay, but then now I've just told you that the surface charge density sigma should be axisymmetric, right? And since it is axisymmetric, the only way to write it down is as a Hankel function integral. I mean, the only way, as in the most convenient integral representation, is the Hankel function integral, right? Which is just, say, sigma of k perpendicular j naught k perpendicular rho e to the minus k perpendicular mod z by 2 k perpendicular epsilon naught, right? Right? Okay. Note that, I mean, note that I've done nothing really new here, right? The insight I've used is basically the fact that above the plane, all you really need to solve is the Laplace equation, right? Except for this point charge, which already solves for the Poisson part of the equation. The source is already taken care of because the equation you need to solve is the Poisson equation with a point charge at z naught. Okay, but the point charge at z naught is already handled by this. So the rest of this equation, the rest of the solution must be a solution of the Laplace equation, right? It's the homogeneous solution. Okay, and if you want to solve a Laplace equation with the boundary condition that as you go higher and higher in z, as you go infinitely far away from the point charge and the plane, the solution should really go to 0, right, on both sides of the plane. And the only way to make sure of that is to put an exponential damping. Okay, so you're basically solving a 3D Laplace equation. Okay, but then it goes to 0 as z goes to infinity. So you write down a solution like, okay, let's just solve it above the plane. Then you just write down a solution like e to the minus k perpendicular z. This k perpendicular to some arbitrary number. and z greater than 0, as z goes to infinity, it has to go to 0, so you put some exponential. And the other the function outside should just be a function of rho, because it's an axisymmetric problem. Can't be a function of phi, right? So then the 3D Laplace equation for phi implies a 2D eigenfunction equation for f plus k perpendicular squared f equal to 0. Okay. And the only solution for this, such that f is just a function of rho and not of phi, is f equal to j naught k perpendicular. And this k perpendicular is arbitrary, so the solution to the 3D Laplace equation should be some j k perpendicular rho e to the minus k perpendicular z, and you can put some arbitrary function of k perpendicular and then integrate it over all k perpendicular. This is the most general form of this homogeneous part of the solution, and that's all I've done. The rest is just some normalization which we'll see to be convenient in a moment. Okay. The normalizations are convenient, so I put those normalizations. If you don't want to put it, you can just write it like this. Okay. The real interpretation is that this A, when you write it in this normalization, the sigma is the induced surface charge density. Okay, so I'm going to erase this. Okay, so now question is, how do you find the sigma, right? Once you find the sigma, you're done, because that is the solution. Okay, and you've also found the surface charge density, because that's what sigma is. Okay. So how do you do it? You just use the boundary condition, and the boundary condition here is that at z equal to 0, the potential has to vanish. Okay, so phi of rho comma z equal to 0 is 0, which implies that minus q over 4 pi epsilon naught square root rho squared plus z naught squared equal to integral 0 to infinity k perpendicular dk perpendicular over 2 pi sigma of k perpendicular over 2k perpendicular epsilon naught times j naught of k perpendicular rho, right? Because z equal to 0. Okay, we just have to solve this, invert this equation to find the sigma, but inverting this equation is easy, right? There are multiple ways to invert this equation, but one way is to just notice that the Hankel transform, this J naught transform, is really a Fourier transform, so you just need to invert the Fourier transform. Okay, if you remember that trick from a few classes ago when we were doing this axisymmetric problem. Or if you remember this axisymmetric problem, one of the main results of the axisymmetric problem, and when I had also mentioned that we'll use that in the method of images, it's used to derive the method of images, is a particular integral representation of this Coulomb Green function, which if you remember is that 1 over 4 pi square root rho squared over rho squared plus z squared is equal to integral 0 to infinity k perpendicular over 2 pi j naught k perpendicular rho e to the minus k perpendicular mod z over 2k perpendicular. Okay. So this is an integral representation of Coulomb Green function. Right? So you can just use this integral representation and then just compare both sides. Okay? And use the fact that J naught is some J naught at different k's are independent. Okay? So if you put this in here, what do you get? You get integral 0 to infinity k perpendicular dk perpendicular over 2 pi J naught of k perpendicular rho, where at z greater than 0, so mod z is just z. Okay, remember that. And z naught is positive. So you get minus q over epsilon over 2k perpendicular epsilon naught e to the minus k perpendicular z naught, that's this side of the equation, equal to integral 0 to infinity k perpendicular dk perpendicular over 2 pi j naught of k perpendicular rho sigma of k perpendicular over 2k perpendicular epsilon naught. Yeah. Comparing both sides of this equation, you can just compare both sides of this equation, and the 2k perpendicular to epsilon naught cancels. So you just get that sigma of k perpendicular is equal to minus q e to the minus k perpendicular z naught. Okay. So what does that mean? That means that finally the answer for the potential everywhere can just be written as q by 4 pi epsilon naught square root rho squared plus z squared, sorry, z minus z naught whole squared plus integral 0 to infinity k perpendicular dk perpendicular over 2 pi. Sigma of k perpendicular, which I just found, is just some minus q e to the minus k perpendicular z naught j naught k perpendicular rho e to the minus k perpendicular mod z, but mod z is just z because we are solving for z greater than 0, we are solving above the plane, over 2k perpendicular epsilon naught. But notice that this is in the form of the integral representation that I wrote down a minute ago. So you can just rewrite this as the following. That's just the first piece. Minus q integral 0 to infinity k perpendicular dk perpendicular over 2 pi j naught minus q I took outside, and you have minus k perpendicular z plus z naught over 2k perpendicular epsilon naught. And this, you can write it in this form. So the answer becomes q over 4 pi epsilon naught square root rho squared plus z minus z naught whole squared minus q over square root, sorry, 4 pi epsilon naught square root rho squared plus z plus z naught whole squared. Okay. And that's the method of images, right? Because basically what it says is that the potential everywhere is equal to the potential due to a point charge, which is q times point charge q, which is q times the Coulomb Green function at rho comma z naught. Sorry, Coulomb Green function for a charge at z naught minus q Coulomb Green function for a charge at minus z naught. Okay, where the Coulomb Green function is just 1 over 4 pi epsilon naught square root rho squared plus z minus z naught. Okay, but basically you just have to get in here, right? So that's the method of images. It basically says that the potential everywhere, which is due to this point charge above the conducting plane, as well as the surface charge density induced on the conducting plane, is basically just equal to a point charge, that original point charge, but the surface charge density acts basically like a negative point charge at the mirrored point at minus z0. And that is the method of images. Okay. So you see how straightforwardly the method of images can be derived as long as you know this J naught representation of the Coulomb Green function. Okay. So this J naught representation, or this Hankel function representation of the Coulomb Green function, which it derived and we saw the logic of. Okay. So let me just explain this integral representation once more, because the integral representation is what is crucial to this method of images problem, right? But remember that we got this integral representation by doing this ring charge problem and taking the radius of the ring to 0 and getting a point charge, right? But basically, the point is that you're solving the Laplace equation for everywhere else. Sorry, let me say that again. If you have a point charge at the origin, okay, then basically you're solving the Laplace equation everywhere except the origin. And at the origin, you have some delta function. Okay, that's what the point charge means. Okay. Now, since this is a problem in which as z goes to infinity and z goes to minus infinity, you want the potential to die away, you have to put some exponential. Okay, that's some ansatz for the potential. You're solving some 3D Laplace equation, so you write phi equal to some function times exponential. But that some function times exponential, that some function now would have to solve the 2D Laplace equation. 2D eigenfunction equation of the Laplacian, okay, with a negative eigenvalue. But then it also has to be axisymmetric, right? Symmetric about rotations about the z-axis, because it's just a point charge at the origin, okay? And the only such solution is just J naught, okay? And the rest of the integral you just find by doing the correct normalization. Okay? I'm just reminding you why this answer was correct. The rest of the normalization you just have to fix by doing that problem. But anyway, so this integral representation, this Hankel function representation, is what actually gives you the method of images. So for this derivation of the method of images, you can look at Zangwill. Okay. So now the conducting plane is sort of easy. Let's move from the conducting plane and let's try to ask, what about the dielectric? Okay. Can we get this method of images solution for the dielectric? Okay. Let's do that. Semi-infinite dielectric. Better. Still dielectric block. Okay. So the problem I want to consider now is again a Griffiths problem. You have some z-axis, and this is the z equal to 0 plane. Above the z equal to 0 plane, you have epsilon naught, and below the z equal to 0 plane, you have some epsilon. Okay. Now the question is, you put a point charge q at some z naught. What is the potential everywhere? Okay. Again, even this problem, there are multiple ways of doing it. Griffiths does it in two different ways. One of the ways in which Griffiths does it is to use the method of images and to say that there is some point charge qb at minus z naught, and he gives some value for the qb and says this is the answer, right? Now the question here is, how do you derive that? Okay. Now I'm going to start using this Hankel function representation of axisymmetric problem for axisymmetric problems without warning. Okay, so I'm just going to write it down because we have learnt it and we have seen it multiple times. Okay, so here again, since the problem is axisymmetric, the final potential can be written as the potential due to this q and the potential induced by the surface charge induced on the surface of the dielectric, right? So the answer should be q by 4 pi epsilon naught square root rho squared plus z squared plus the thing, the potential induced due to the dielectric, sorry, due to the surface charge at the dielectric, which is, for which you can write such a representation because it's axisymmetric. This is just some normalization times some sigma k perpendicular. Okay, let me explain that further. So the point is that once you put a point charge above a dielectric, the point charge has some electric field, some 1 by r squared electric field in the absence of the dielectric. Now you put the dielectric there, the dielectric will get polarized because of this electric field, right? Right, because it's some linear dielectric, the polarization should be some electric susceptibility times the electric field, right? Right, because P is some epsilon naught chi e times E. So there's some polarization, and that polarization can be thought of as some bound charge within the dielectric and some surface charge. Okay, in such problems the bound charge goes to 0, but there is some surface charge. Okay. This clear? Because remember that within the dielectric, so the bound charge rho b, if you remember, is just some minus divergence of the polarization, okay, within the dielectric. But then within the dielectric, the point is that divergence of the electric displacement is 0 because there's no free charge. Remember that divergence D equals rho f is one of the Maxwell equations, but rho f, which is the free charge density, is 0 inside the dielectric because we are not putting a free charge inside the dielectric. Now since divergence D equal to 0, that would just mean that divergence of epsilon, which is some constant, so you can take it out, times E equal to 0. But that should also mean that you can multiply this by, you can get rid of this epsilon, multiply by epsilon naught chi e, take it inside, so you'd get divergence P equal to 0, which means rho B equal to 0. Okay. So bound charge density is 0, but there is a surface charge density, which is just P vector dot En hat, the normal on the surface. Okay. So basically what happens when you put a dielectric and an electric field is that you get some bound charge and you get some surface charge. In this case there is no bound charge, okay, because it's some constant permittivity inside, so by this derivation there's no bound charge inside, but there's some surface charge, sigma b. Okay, and that's the surface charge, okay, which I can write in some Hankel function representation with the J naught because it's an axisymmetric surface charge density. Okay. Okay, great. So now this I can rewrite using the Hankel function representation for this part as integral 0 to infinity k perpendicular d k perpendicular over 2 pi j naught k perpendicular rho. Sorry, this is z minus z naught whole square. I'm sorry about that. You get e to the minus k perpendicular z minus z naught over 2k perpendicular epsilon naught. That's this bit plus e to the minus k perpendicular mod z sigma k perpendicular over 2k perpendicular epsilon naught. Okay. So now question is, how do you find the sigma? As usual, you use the boundary conditions. What is the boundary condition here? The boundary condition here is the one at the surface of the dielectric, right? At the surface of the dielectric, what do you have? You have the fact that, okay, let me derive the boundary condition for you. You have divergence D equal to 0, okay, which basically means divergence of epsilon of Z E equal to 0. Epsilon is just a function of z, which basically means that below z equal to 0, epsilon of z equal to epsilon. Above z equal to 0 is just some epsilon naught vacuum, right? Now this, if you integrate about a pillbox, which is around the surface, you basically get that Ez hat dot epsilon of z e vector minus Ez hat, the other surface of the pillbox, epsilon of z e vector equal to 0, which basically means that Ez hat dot epsilon of z grad phi from minus equal to minus Ez hat dot epsilon of z. This is at z equal to 0 plus, z equal to 0 minus, z equal to 0 plus, grad phi, z equal to 0 minus. Okay. So the boundary condition really is that epsilon at z equal to 0 plus, epsilon of z is just epsilon naught del z of phi at z equals 0 plus equal to epsilon del z of phi at z equal to 0 minus. That's the boundary condition. So you just have to put this answers that we derived into that boundary condition, right? So putting this solution into this boundary condition, what do you get? You get epsilon naught. Now you have to do del z of phi at z equals 0 plus. So you get 0 to infinity, k perpendicular, dk perpendicular over 2 pi, j naught k perpendicular rho, e to the minus k perpendicular mod z minus z naught when z equals 0 plus is just e to the minus k perpendicular of z naught minus z. So once you differentiate, you get a k perpendicular and you get e to the minus k perpendicular z naught over 2 epsilon naught. Now you come to the second term, that gives you a minus k perpendicular, right? So you get e to the minus k perpendicular becomes 1 over 2 epsilon naught, and then you get a sigma k perpendicular. Okay, that's this side of the equation, equal to epsilon integral 0 to infinity k perpendicular dk perpendicular over 2 pi j naught. First term remains the same because that's a mod z minus z naught, whether you're above z equal to 0 or z below z equal to 0, it doesn't matter to that term. So you get, I think I'm missing a q. Yeah, I'm missing a q. There should be a capital Q here. Q e to the minus k perpendicular z naught over 2 epsilon naught. Okay. Now second term, when z is equal to 0 minus, e to the mod z is just minus z. So you get plus sigma of k perpendicular over 2 epsilon naught. Okay. Now comparing both sides of the equation, you get some linear equation. Okay. And that's the miraculous part. When you're using this Hankel transform, at the end of the day, all you need to solve is linear equations. Okay. So comparing both sides, you get an equation of the form q over 2 epsilon naught. Let me cancel the epsilon naught on both sides. Q over 2 e to the minus k perpendicular mod z, sorry, e to the minus k perpendicular z naught minus sigma of k perpendicular over 2 equal to q e to the minus k perpendicular z naught epsilon by epsilon naught plus sigma. Yeah, which implies that sigma of k perpendicular, I'm missing a 2. Yeah, the 2 from both sides go away. So you get sigma perpendicular into 1 plus epsilon over epsilon naught equal to q e to the minus k perpendicular z naught into 1 minus epsilon over epsilon naught, which implies that sigma of k perpendicular equal to q e to the minus k perpendicular z naught times epsilon naught minus epsilon by epsilon plus epsilon naught. And let me write that finally as sigma of k perpendicular equal to minus q epsilon minus epsilon naught by epsilon plus epsilon naught e to the minus k perpendicular z naught. That's sigma of k perpendicular. Now all you need to do is to put that into the ansatz we wrote down to get the final solution. Let me do that now. Okay. So let me come beginning. So the final potential in that problem becomes, remember that you had a q by 4 pi epsilon naught square root rho squared plus z minus z naught squared. Okay. And the rest of the thing we wrote is 0 to infinity k perpendicular dk perpendicular over 2 pi j naught mod z just becomes z. Let's solve it in z greater than 0. Z greater than 0 over 2k perpendicular epsilon naught. And then you get sigma of k perpendicular, but sigma of k perpendicular I just found, remember, is just some minus q, epsilon minus epsilon naught by epsilon plus epsilon naught, e to the minus k perpendicular z naught. Okay. Now what does that say? E to the minus k perpendicular z and e to the minus k perpendicular z naught just becomes e to the minus k perpendicular z plus z naught. You can put a mod if you want because you're in z greater than 0. So this is basically, now again I will use the hankel-transform representation of the Coulomb green function to write this as and then you have a minus q epsilon minus epsilon naught by epsilon plus epsilon naught. Okay. And then since the exponentials add up, the rest just becomes a Coulomb green function. At minus z naught. Okay. Again, we have some method, we have some image charge. Okay. Therefore, image charge q, let's call it image equal to minus q epsilon minus epsilon naught by epsilon plus epsilon naught at z equal to minus z. Okay. So even in this dielectric problem, we have found that you can do it as a method of images problem. Okay. And the image charge is something like this. Okay. Okay. So that's wonderful. So we have solved a conducting plane problem and a dielectric problem using this hankel-transform representation, and we have just reduced it to some image charge problem. Now you might ask sensibly, what if we take a problem that looks like this? You take some dielectric slab, some epsilon, epsilon naught, epsilon naught. If you start solving this with method of images, if you didn't know this hankel-transform representation and so on, if you just start solving this with method of images, you would have to, and if you put some point charge q here by the way, you would have to reflect this point charge about the first plane and then about the second plane, and then those reflections themselves must be reflected about both the planes, and you'll get an infinite lattice of point charges, okay, with alternating sign and at different positions. And if you want to solve this problem, you would have to find this full infinite set of charges and add the potential due to all of them, right? And now if you make this problem more complicated and say you have two dielectric slabs at some epsilon 1, epsilon 2, epsilon naught, and you put a point charge q there, it becomes far more complicated. You have three different mirrors to reflect about, okay, and you keep reflecting and you get a full, again you get an infinite lattice of infinite 1D lattice of point charges with alternating sign, and you have to add all of them up to actually solve this problem. Okay. But if you now cleverly don't use the method of images, instead use this hankel-transform representation, notice that once you use the hankel-transform representation, you just have some point charge, you just have some surface charge density on this surface charge density on this surface. You write some hankel-transform representation for both of them, and you just have to find that sigma 1 and sigma 2, for which you just have to use boundary conditions at this plane and this plane. Right? And as we have seen, once you write it in this J0 representation, all of the J0 and the integral and so on go away, and you get some linear equation to solve. In this case, you'll get 2 linear equations. In this case, you'll get 3 linear equations. And depending on the number of surfaces you have, you get, if n is the number of surfaces, you get n linear equations. And linear equations anybody can solve. You can just put it in a computer, solve it. Symbolically. You can put it in Mathematica and solve it. Right? So that's the real power of using this hankel-transform representation. So next time, I will actually solve this dielectric slab problem, okay, and show you that this dielectric slab problem can also be written as a method of images problem, and I will derive for you this infinite sequence of point charges. Okay, this dielectric slab problem can be solved with just one charge, but for simplicity, next time I'll solve it with plus q and minus q here, so that I just have to find one surface charge density and use symmetry to find the other surface charge density. You can solve for both, of course. Okay. Okay, so I'll stop here then. Thanks.